Something is happening out there in the dark, quiet, almost invisible, yet extraordinary. Every few decades, the universe sends us a messenger from beyond, a silent traveler that slips through our solar system carrying stories written in starlight. Before we begin tonight's journey, take a slow breath. Let the world around you fade and allow the noise of the day to settle. Because this story unfolds in silence, in the hush between stars, where motion itself becomes a whisper. Welcome to Science Reshaped, a calm corner of the cosmos where your thoughts can drift weightlessly, and science becomes a soft voice guiding you through wonder. Before we continue, please take a moment to subscribe to Science Reshaped and tell us where in the world you're listening from. It's always humbling to see how far these quiet stories travel, across time zones, cities, and midnight skies. Tonight, we follow a visitor unlike any we have known before, an interstellar traveler named 3I Atlas. At first, it appeared ordinary, a faint speck gliding against the background of Pisces, barely distinguishable from the endless dust of space. But something about it refused to behave as expected. The numbers, the equations, even the carefully calculated orbits began to slip out of alignment. The object wasn't just moving, it was accelerating. Telescopes confirmed what the data had whispered. 3I Atlas was gaining speed. No error, no faulty instrument. A small but measurable force was pushing it, defying the clean predictability of Newton's gravity. That acceleration was almost imperceptible, just 0.02 millimeters per second squared. Yet across the vast canvas of space, such a gentle nudge becomes enormous. Over days, then weeks, that minute force could shift its path by millions of kilometers. The pattern felt familiar. Astronomers had seen something like this before with Oumuamua, the first recorded interstellar object, whose strange acceleration had sparked debate, excitement, and mystery. Now, years later, another wanderer showed the same delicate signature. Late in 2024, the Atlas survey telescopes in Hawaii spotted it first, a dim, fast-moving point of light entering the inner solar system from deep space. Its speed, about 60 kilometers per second, told scientists that it wasn't bound to the sun. It was a guest from another star, here only once. Through early 2025, observatories tracked its curved hyperbolic path, but soon those predictions began to drift. The expected positions no longer matched reality. Telescopes in Chile, Spain, and Japan all confirmed the same deviation. Perhaps they thought it was a comet venting gas as sunlight warmed its frozen crust. But no coma appeared, no shimmering tail, no trace of vapor. Spectrographs showed nothing but silence. If sunlight alone was responsible, its surface would need to be thin and mirror-like, reflecting photons with unnatural efficiency. That too seemed unlikely. And yet the acceleration persisted, steady, consistent, undeniable. Over 50 days, this faint extra push amounted to roughly 86 meters per second of added velocity, only a fraction of its total speed, but enough to redraw its orbit. The new trajectory ran just beside the old one, a small divergence that hinted at something subtle and unknown. In space, even whispers matter. Whatever was acting on 3I Atlas wasn't gravity, wasn't gas, and wasn't light alone. It was something else, a faint physical truth still waiting to be named. So tonight, as we drift deeper into the mystery, we do not chase fear or speculation. We simply listen to the data, to the silence, and to the stories carried by travelers between stars. This is Science Reshaped, and this is where the story begins. The more scientists observed 3I Atlas, the stranger it became. By mid-year, orbital data from multiple observatories showed that the object's path didn't perfectly match the clean curve predicted by Newtonian gravity. Something else was nudging it, ever so slightly, in a direction that equations alone couldn't explain. Teams across the world began comparing notes. Data from the Atacama Desert in Chile matched results from Mount Palomar and La Silla. No matter who measured it, the residuals, those tiny differences between where the object should be and where it was, remained. A consistent acceleration, faint but persistent, pressed against it. That realization caused a ripple through the astronomical community. Whenever numbers refuse to behave, there are only two possibilities. The measurements are wrong, or the universe is telling you something new. And here, the data refused to break. analysts fed the readings into orbital determination models, adjusting for solar radiation, planetary tugs, even the pull of Jupiter's mass far beyond. Yet the unexplained acceleration stayed fixed at roughly 0.02 millimeters per second squared, directed slightly sideways relative to the Sun. Not inward, not outward, sideways. In cosmic navigation, that single detail changes everything. A tangential acceleration means the object's speed and heading are both shifting. If it had been a comet venting gas, the push should point directly away from the Sun, just as a jet of vapor would. But this one defied that rule. As the new coordinates were plotted, its orbit lengthened. Just a touch, but enough to alter the projected missed distance for future months. Calculations showed that if this faint force continued at the same rate, the trajectory could drift by millions of kilometers before the year's end. Astronomers weren't sounding alarms. They were sharpening pencils. Every update required recalculating the ephemeris, those precise time-stamped positions used to aim telescopes. Night after night, they watched the object's path crawl across the star field. A delicate arc that no longer followed the earlier predictions. It was as though an invisible hand were tracing a slightly new route through the void. Meanwhile, telescopes searched for any sign of visible activity. If the acceleration came from outgassing, a thin envelope of vapor should surround the body, scattering sunlight into a faint halo. But even in deep exposures, the object remained a single sharp point. No blur, no tail. Instruments scanning in infrared and ultraviolet wavelengths found nothing that could account for the motion. A few scientists proposed that the object might be unusually reflective. Its surface, composed of material that caught sunlight more efficiently than expected. Radiation pressure from photons could indeed push an object, but only if its surface-to-mass ratio were extreme. For 3I Atlas, the math suggested something like a sheet of metal only millimeters thick. Nature doesn't usually craft such things. Still, researchers refused to leap to conclusions. The story of Oumuamua had taught them how quickly speculation can outrun data. They stayed patient, gathering more light curves, more positional points, more nights of tracking. Each measurement, each dot plotted against the stars, tightened the error bars, and still the anomaly persisted. By late summer, the object had passed its closest point to the Sun, yet the unexplained acceleration showed no sign of fading. Instead, it remained steady, like a soft pressure guiding it along an unseen path. In the language of orbital mechanics, this meant that its trajectory after perihelion, the outbound leg, would diverge even more from the inbound track. When plotted on a graph, two lines appeared, the expected orbit and the real one. The difference between them might look small to the human eye, but across tens of millions of kilometers, it was enormous. The implication was clear. Some additional energy was being introduced into the system. No one could yet say from where, but the data were now solid enough that the question had to be asked aloud. What kind of force, gentle yet constant, could accelerate a cold, airless fragment drifting between stars? Weeks turned into months, and the observations continued. Each new dataset confirmed the same quiet truth. The object was still accelerating. Nothing had changed in its physical appearance, and still, the numbers told a different story than gravity alone could explain. Every night, as telescopes traced its light, astronomers plotted the difference between its predicted position and the one recorded by their sensors. Those small discrepancies, fractions of an arcsecond, were now too consistent to ignore. The acceleration wasn't random, it was patterned, continuous, and measurable. The direction of that subtle force, once again, didn't align with any standard model. It wasn't purely radial, nor was it caused by a gravitational encounter with any nearby planet. The data showed a consistent lateral push, almost as if something invisible was gliding alongside it. To rule out error, researchers recalibrated every factor they could. They compensated for sunlight pressure, for Earth's orbital motion, even for background light distortions from other stars. Yet the residual acceleration stayed fixed. If it had been a comet, outgassing could explain the shift. But even that theory fell apart under closer inspection. Normally, outgassing creates a coma. Jets of vaporized ice escaping as heat rises, pushing the nucleus like tiny thrusters. But for 3I Atlas, there was no visible gas, no plume, and no photometric variation to suggest venting. The object seemed cold, inert, and yet somehow in motion. What puzzled scientists most was its steadiness. Outgassing, when it happens, fluctuates depending on the object's rotation and exposure to sunlight. The thrust direction changes as different regions warm and cool. 3I Atlas, however, maintained a nearly constant push, unchanging even as it turned and drifted away from the sun. By early autumn, the trajectory models were split into two, the purely gravitational curve and the adjusted curve accounting for the measured acceleration. On paper, the difference appeared minute, a deviation of only a few thousandths of a degree, but extrapolated months ahead, the two lines diverge by millions of kilometers. In celestial mechanics, small forces create vast outcomes. A feather touch repeated endlessly can turn into a storm. Simulations projected where 3I Atlas would be in late December of 2025, when it would make its closest approach to Earth's orbit. The numbers placed it at roughly 1.8 astronomical units, still far, well beyond Mars, but closer than initial estimates. Not a danger, not even remotely, yet close enough that the data had to be exact. That realization triggered another wave of observations. Observatories in Arizona, Spain, and Chile coordinated time slots to ensure continuous coverage. Each telescope added one more point to a growing arc of precision. The more points they gathered, the more the mystery solidified. By now, 3I Atlas had become one of the most observed interstellar objects in recorded history. Yet the more attention it received, the more questions it raised. Its brightness barely changed as it passed perihelion. Its rotation appeared slow, perhaps taking many hours to complete one spin. No tumbling, no flashing glints of reflected light, just a steady, calm movement through space. It was as if the object was built for stability, shaped to move without losing balance. No one dared to draw conclusions. The story of its motion would be told by physics alone, not by imagination. And so, night after night, astronomers watched it slip farther from the sun, continuing its quiet acceleration toward the edge of the inner system. In their notebooks, they recorded the same questions again and again. If it's not gas, and it's not light, what else could push an interstellar rock through space? By late autumn, a pattern began to take shape. The acceleration, though minuscule, was steady enough that scientists could map its influence over time. Each recalculation refined the orbit, and each refinement brought a new realization. This wasn't an isolated incident. When astronomers compared 3I Atlas's motion to that of Oumuamua, the first interstellar object detected years earlier, they saw eerie similarities. Both had displayed non-gravitational acceleration of nearly identical strength. Both lacked visible tails or any sign of gas release. Both entered the solar system on hyperbolic paths, moving too fast to be captured by the sun's gravity. The two trajectories were separated by years and vast distances, yet the physics seemed to rhyme. This repetition forced scientists to revisit the old equations they had once used to explain Oumuamua. They tested radiation pressure again, plugging in the mass and reflectivity estimates that had been debated endlessly online. The numbers worked, but only if the object's density was extremely low, lighter than air, almost hollow. That didn't fit a natural rock or chunk of ice. And yet, with 3I Atlas, the pattern persisted. The object's brightness curve showed no major variation, suggesting it wasn't tumbling or spinning chaotically. It moved with a stability rarely seen in small celestial bodies. If it were truly a fragment of frozen rock, sunlight should have caused uneven heating, producing momentary surges of acceleration. But its pace remained smooth, as though guided by an internal rhythm too precise to be random. Astronomers, cautious as always, stuck to what could be proven. They continued to describe it as a cometary body, an icy remnant from another system, behaving oddly under solar influence. But in research notes and quiet discussions, many admitted they didn't know. The lack of a tail, the constant acceleration, the flawless stability, it all resisted easy classification. At the European Southern Observatory, one research team focused on its spectral signature, the light it reflected. If outgassing were present, they should have detected specific emissions from carbon, oxygen, or hydroxyl radicals. But the readings came back flat. No lines, no identifiable molecules, only a featureless reflection consistent with an inert surface. That raised another question. If it wasn't shedding gas, and its surface wasn't metallic or highly reflective, then what exactly was causing that push? Could there be something beneath the surface? Some slow reaction or trapped volatile material leaking invisibly into space? Another group proposed the micron dust hypothesis, that fine grains embedded in the surface could absorb sunlight unevenly, creating a continuous microforce as they warmed and cooled. It was plausible, but still too small to explain the observed acceleration. Every hypothesis met the same end: reasonable on paper, insufficient in reality. By November, the object had already passed the Sun and was moving outward, yet the acceleration showed no sign of fading. Even with decreasing solar radiation, the subtle force remained constant. That single fact ruled out most natural explanations. In simulation software, orbital analysts plotted its new course. The projections showed it moving on a stretched hyperbola, its outgoing path diverging slightly from the one it had entered on. If the same acceleration persisted for several more months, the missed distance from Earth would shift again, still safe, but enough to draw continued observation. For now, the consensus was simple but incomplete. 3I Atlas was accelerating, and the cause was unknown. The scientific method leaves no room for comfort. It demands patience, proof, and time, and so the world of astronomy watched in silence, gathering light from a traveler that refused to obey gravity alone. Far beyond telescopes and theories, a single, small object drifted between the planets, steady, silent, and ever so slightly faster than physics allowed. By December, the mystery surrounding 3I Atlas had reached every corner of the scientific world. Data continued to arrive from observatories across multiple continents, all pointing to the same unchanging truth. The object was still accelerating, slowly but steadily, even as it moved farther from the Sun. That fact alone defied what should have happened. Normally, any non-gravitational acceleration caused by solar radiation or sublimation decreases sharply as an object leaves the inner solar system. The farther it travels, the weaker the sunlight, the gentler the push. Yet in this case, the opposite seemed to be happening. The acceleration was not fading away as expected. The European Space Agency's orbital mechanics team began releasing updated plots. Each new trajectory line edged slightly away from the previous one, forming a delicate fan of possibilities. At small scale, the difference looked trivial, but when translated into distance, it meant several million kilometers of deviation between predicted and observed paths. No one suggested danger. The calculated miss distance still placed the object well beyond Earth's reach, but the consistency of its deviation demanded explanation. In research notes, astronomers wrote phrases like non-gravitational vector persistent beyond heliocentric norm. That was scientific shorthand for something simple yet deeply strange. Something was still pushing. As 3Psi Atlas drifted outward past the orbit of Mars, its reflected brightness began to wane, but the precision instruments tracking it still found the same faint acceleration. The pattern had become almost elegant, smooth, continuous, and predictable, as though whatever was driving it operated with perfect stability. Several teams tried once more to fit the observations into known physics. Could the shape of the object be affecting its motion? If it were unusually flat or elongated, the pressure from sunlight might behave differently. Yet, for that to work, it would require a density lighter than anything found in natural space rocks, something more like aerogel than stone. Others turned back to the dust sublimation theory. Maybe it was shedding particles invisible to telescopes, each one too fine to produce a visible coma, but numerous enough to act like microthrusters. But again, the numbers failed to match the measured speed change. Even more puzzling was the object's rotation, or lack of it. Brightness curves hinted at a slow, almost stately spin, with no irregular flicker. The steadiness of that rotation meant that if it were venting gas, the force would have shifted direction over time. The data showed no such wobble. The deeper scientists looked, the quieter the mystery became. No loud evidence, no dramatic signs, just the faint arithmetic of motion defying what gravity alone could do. Each updated report reaffirmed the same theme. An object from beyond our solar system, moving through space, gaining speed for reasons no one could yet explain. For the community of researchers watching, it was both humbling and unsettling. They were not witnessing chaos, but precision. A tiny, flawless push continuing in the same direction, unchanged even as sunlight weakened. The equations grew longer. Computers plotted endless variations. Yet every simulation ended with the same conclusion. Something gentle, invisible, and constant was still at work. And so, night after night, observatories continued to point toward the fading light of 3I Atlas. tracing the quiet trail of an object that refused to behave like anything ever seen before. As 3I Atlas moved deeper into the outer solar system, astronomers adjusted their expectations. If the faint acceleration were caused by solar pressure, it should begin to fade. The light and heat that might once have touched its surface now weakened with distance, dropping sharply beyond the orbit of Mars. Yet when the measurements came in, the numbers stayed almost exactly the same. That result unsettled even the most cautious researchers. The acceleration was supposed to fall by half at least, once the object reached that far. Instead, it held steady, as though the source of the push were completely independent of the sun's diminishing influence. Once again, teams reanalyzed every parameter that could introduce error. They rechecked calibration standards, atmospheric corrections, even the timing software that synchronized telescope data with atomic clocks. Every control test came back clean. The acceleration was real. At this point, the data set was large enough to reveal a clear pattern in direction. The push came neither from the sun nor from the object's motion itself. It seemed to act at a consistent angle, fixed relative to its path. That steady geometry meant it wasn't a random environmental effect like solar wind gusts or magnetic interaction. It had coherence. A few theorists, still anchored in traditional physics, revisited the outgassing model one more time. Maybe the gas escaping was invisible because it was neutral, free of ionized molecules that telescopes could detect. But the amount required to sustain that acceleration would have depleted the object quickly, and yet the readings remained stable week after week. By early 2026, the reality was unavoidable. The behavior didn't fit any known category. It wasn't purely cometary, nor was it purely asteroidal. It was something in between. Something that crossed the boundaries scientists usually draw to classify celestial bodies. In private discussions, some researchers began calling it a silent reactor. Not because they believed it was artificial, but because it seemed to operate by rules hidden within its own structure. Its surface, its mass distribution, its interaction with radiation, all of it combined to produce a motion that no single explanation could fully capture. And yet, despite the growing sense of confusion, there was also wonder. Here was an object, no larger than a small mountain, that had traveled from another star system, entered ours, and left behind a mystery that stretched across every telescope and laboratory that studied it. By mid-February, 3I Atlas had grown too faint for smaller observatories to follow. Only the largest instruments, those perched on high-altitude plateaus and orbiting above Earth's atmosphere, could still see its thin line of reflected light. But even as it faded, the acceleration signature could still be measured. The data log showed the same slope, the same angle, the same slow drift. Nothing had changed since its first recorded anomaly. For the scientists still tracking it, each faint detection felt like a heartbeat, steady, unhurried, impossible to ignore. And so the story continued, one frame at a time, as 3I Atlas slipped quietly away into the vastness that had once sent it here. By the time winter arrived, 3I Atlas had crossed beyond the region of the inner planets. Its faint light was barely detectable, yet astronomers continued to follow it with unwavering precision. Each night's data fed into central databases, where computers compared the latest readings to thousands of earlier measurements. The results remained constant. The acceleration was still there, gentle, steady, and unexplained. It was now far past the orbit of Mars, moving into the colder and thinner reaches of the solar system. Sunlight there was weak, nearly 1/10 the strength it had been near Earth's orbit. Under normal physics, any non-gravitational acceleration tied to sunlight or gas emissions should have nearly vanished by now. But the equations refused to bend. The same small push persisted, indifferent to distance. Teams in the United States, Europe, and South America worked together to combine observations from different nights, stacking them to enhance the faint signal. The more they did, the clearer the trend became. The data pointed not to error, but to reality. The object was being acted upon by a continuous force that could not be explained by any standard model. Astronomers adjusted for every conceivable source of interference. They ruled out cosmic rays, instrument drift, atmospheric distortion, even the gravitational effects of minor asteroids. None of it changed the result. The math stood firm. Among researchers, two main possibilities remained on the table. One was physical, that 3I Atlas contained some ultra-volatile substance venting invisibly, a form of sublimation so fine that even advanced sensors could not catch it. The other was mechanical. that its shape or surface properties were interacting with radiation in a way never before seen in a natural object. Both were unlikely. Both failed to explain the constancy of the effect. Despite all efforts, no telescope, no spectrograph, and no radar system had found the slightest hint of a tail or halo. The object remained what it had always been, an unchanging point of light crossing the sky. By now, the fascination surrounding 3I Atlas had extended far beyond professional circles. Amateur astronomers followed its coordinates nightly, while science communicators tried to explain its behavior in simple terms. But even simplified, the truth was strange. A rock or fragment from another star system was being pushed through space by something we still could not define. The more scientists tried to frame it, the more elusive it became. If they described it as a comet, it disobeyed every known rule of cometary motion. If they called it an asteroid, it moved like no asteroid ever had. If they assumed radiation pressure, the required surface area was far too large to be natural. By early 2026, the official bulletins listed it as an interstellar object with non-gravitational acceleration of unknown origin. It was a careful phrase, neutral but profound. It said everything and nothing at once. Some researchers suggested waiting another few months. If the acceleration was caused by sunlight, it would eventually fade as the object slipped beyond Jupiter's orbit. The next few observations would tell. If the numbers stayed the same even there, something truly remarkable was happening. And so, every week, telescopes continued to point at the faint coordinates in the dark. Each new measurement, tiny, uncertain, but invaluable, was added to the growing record of a journey that challenged the simplest law of motion. Atlas was still accelerating, still moving silently, and still rewriting what scientists thought they knew about the behavior of interstellar visitors. In the months that followed, 3I Atlas drifted farther from the Sun, slipping into regions where light grows thin and warmth fades to nothing. The object was now moving through the outer solar system, beyond the reach of even the most powerful ground-based telescopes. Only the largest instruments, including space-based observatories, could still track its position with any clarity. Yet even as it moved into the darkness, the acceleration refused to disappear. Every new measurement repeated the same outcome, a faint but measurable push that continued long after solar radiation should have lost its influence. This consistency began to challenge not just individual hypotheses, but the broader framework of how interstellar bodies interact with solar systems they pass through. Each new reading was a quiet contradiction to the laws that had held true for centuries. Some scientists began reviewing the data from older interstellar objects for comparison. They looked again at Oumuamua, analyzing whether its strange acceleration and shape might have been part of a wider pattern rather than an isolated case. And now, with 3I Atlas showing a nearly identical signature, that possibility no longer seemed far-fetched. There was talk of a new classification, objects that showed unexplained motion, neither cometary nor asteroidal. They would require their own models, their own terminology, and perhaps their own branch of celestial study. But before any of that could happen, more proof was needed. Astronomers prepared long-range observation campaigns, planning to follow 3I Atlas for as long as technology would allow. They hoped to capture its trajectory as it left the solar system entirely, to see if the acceleration finally ceased once it escaped the Sun's domain. In a sense, they were watching an experiment conducted by nature itself, an experiment measured in years instead of seconds, carried out across billions of kilometers. Meanwhile, the object had become a quiet fascination beyond the scientific community. News outlets and social media debated what it could mean, often amplifying the mystery far beyond what the data supported. Headlines speculated on artificial origins, alien technology, and unexplainable forces. But within observatories and academic circles, the tone remained careful and deliberate. The evidence was extraordinary, but the conclusions still belonged to ordinary physics until proven otherwise. Still, even the most disciplined scientists could feel the pull of wonder. To see an object cross into our system from another star, to measure its defiance of gravity with such precision, it reminded them that the universe still held secrets waiting to be discovered in the faintest of numbers. As months passed and the data points grew scarcer, a feeling settled in the community. They were witnessing something subtle, something that would likely take years to fully understand. The sky had sent another puzzle, and all humanity could do was follow it as far as light and time would allow. Out there, In the deep quiet beyond Mars, a small fragment of another world was moving faster than it should, carrying within it the unanswered question of how. By the time spring came, 3I Atlas had traveled so far from the Sun that even the largest optical telescopes could barely detect it. Its brightness had faded beyond the reach of most instruments, leaving only a few high-sensitivity observatories to continue the watch. Every remaining data point became precious. Each signal, faint as dust, was treated like gold. And still, the acceleration persisted. Even as sunlight weakened to a fraction of its former strength, the same delicate increase in speed appeared in the trajectory calculations. It was no longer possible to deny it. The effect was real, measurable, and continuing beyond the limits of known explanations. At this stage, astronomers began relying more on predictive modeling than on live observations. The signal was so faint that direct imaging was nearly impossible. Instead, computers projected where the object should be based on the cumulative effects of its measured motion. When telescopes turned to those coordinates, the object appeared almost exactly where the models placed it. That confirmed the acceleration's persistence, even when unseen. But this raised a deeper question. If the sun's light was no longer the driving factor, then what was left? The only remaining force was interstellar in nature, perhaps something within the fabric of space itself influencing the motion of small bodies passing through it. Physicists began to explore extreme possibilities. Could there be a kind of background interaction that only affected objects of specific composition or surface texture? Could something in the interstellar medium create a gentle drag, or, in this case, a push? None of it was certain, but every possibility was worth testing. Despite the expanding mystery, scientists remained calm and methodical. There was no sign of danger, no reason for alarm. The object's trajectory showed it would never approach Earth closely. At its nearest, 3I Atlas would still be nearly 270 million kilometers away, safe, distant, and harmless. Yet even knowing that, curiosity persisted. The idea that something so small could defy the simplest laws of motion fascinated everyone involved. This wasn't a story of risk, it was a story of discovery. Back on Earth, teams prepared for the final observational campaign. They scheduled long exposure sessions during the darkest nights, hoping to gather one last round of precise data before the object faded completely from view. The process was painstaking. The light from 3I Atlas was so dim that exposures stretched for hours, and even then, the signal barely rose above the background noise. But for those who studied it, the effort was worth every second. Each faint image was a reminder that, for a brief moment in time, humanity had been able to measure something from another star, something that crossed through our neighborhood, carrying questions older than our species itself. No one knew how long the acceleration would continue or when it would finally fade. Perhaps it would vanish as it moved into the emptiness beyond Jupiter. Perhaps it would continue indefinitely, as though powered by a principle yet to be written in any physics book. Whatever the answer, 3I Atlas had already done something extraordinary. It had reminded scientists that even in an age of supercomputers and space telescopes, the universe could still whisper mysteries too delicate for certainty, and so, in the quiet of distant observatories, the faint speck of 3I Atlas continued on, drifting into the dark, gaining speed against reason, leaving behind data, silence, and wonder. As the months unfolded, the light from 3I Atlas weakened to almost nothing. It had moved far beyond the orbit of Jupiter now, into regions of space where sunlight was little more than a distant glimmer. The object that had once stirred so many questions was now nearly invisible to the instruments that had tracked it for over a year. Still, the story wasn't finished. Long after the last visible frames were captured, the tracking data continued through mathematical models. Using the previous months of observations, computers simulated its current location, velocity, and acceleration. The virtual projection matched every known measurement so precisely that scientists could still predict where it should be, though no telescope could yet confirm it. That alone was remarkable. It meant that whatever had been influencing its motion remained constant, even far beyond the regions where sunlight could act as the main driver. In physics, that kind of consistency is rare. Small effects fade, natural forces weaken, but this one persisted like a quiet signature in space. A few teams revisited the equations, attempting once more to trace the source of the acceleration. Every possible explanation had been tested and retested. Sublimation, radiation pressure, uneven heating, interaction with solar wind. Nothing fit the data fully. If the cores were outgassing, the rate should have dropped sharply after the sun's warmth diminished. If it were photon pressure, it should have been nearly zero by this distance. Yet the inferred acceleration remained almost unchanged. Scientists turned their focus to material properties. Maybe 3I Atlas possessed a composition so unusual that it reacted differently to temperature or light. Perhaps it was made of compounds or minerals unseen in our solar system, molecules that could hold and release energy in ways unfamiliar to Earth-based laboratories. This wasn't an exotic claim, only a reminder of how limited human experience truly is. Interstellar space could hold materials formed under conditions impossible to reproduce here. Even then, the persistence of the acceleration remained difficult to justify. If the object truly was emitting material, it would eventually lose mass or show rotational instability. Yet both parameters appeared constant. It behaved as though something beneath its surface or within its structure kept a perfect balance of forces. By mid-year, attention shifted from direct observation to theoretical work. Research groups published studies, each exploring a new corner of the puzzle. Some examined the thermodynamics of ultra-cold ices under cosmic radiation. Others modeled how thin layers of exotic dust might create a self-sustaining pressure differential. But all papers ended with the same sentence: the cause of the persistent acceleration remains undetermined. It was an unusual admission for a field that thrives on equations and certainty. But astronomy often begins that way, by confronting data that doesn't yet make sense. For those who had followed the object from its first detection, the feeling was bittersweet. The mystery was still unsolved, but there was a quiet satisfaction in knowing that, for a brief moment, they had measured something unique, something that carried the imprint of another world, another star, another time. Even as 3I Atlas slipped from view, it continued its journey into the black, carrying within its path the faint evidence of an unknown force, an unanswered question left drifting in the cold silence of space. As 3I Atlas faded into the outer dark, data scientists kept refining the models that described its motion. Every minor improvement in the original readings, every recalibrated timestamp, every tiny correction in angular distance was added to the archive. The resulting trajectory became one of the most precisely charted paths ever recorded for an interstellar visitor. But precision didn't erase the question. It only made the mystery clearer. The consistency of the acceleration became its most haunting feature. Over an enormous stretch of space, through regions of differing radiation and temperature, the rate of change stayed almost identical. It was as if whatever was propelling the object cared nothing for distance, light, or energy. To rule out systemic bias, the teams involved exchanged their data sets. The calculations from Japan, Chile, Hawaii, and the European Southern Observatory all produced the same result within the margin of error. Even NASA's Deep Space Network confirmed it through radar correlation analysis. That kind of agreement across independent methods left little room for illusion. The acceleration existed. Scientists began to think differently, not of what was pushing the object, but of what it was. Maybe its internal structure, rather than an external force, was the source of the anomaly. Could the material itself store solar heat in a way that created a continuous release of energy long after the sun's radiation weakened? If its composition were porous enough, sunlight absorbed earlier in its passage could be leaking back out slowly, producing a microthrust invisible to instruments. The effect would be subtle but continuous. The challenge, however, was magnitude. The required thermal retention capacity was orders of magnitude higher than any natural substance known. Still, the idea had merit. In the absence of visible outgassing, thermal re-emission became one of the few remaining physical mechanisms that could explain a sustained non-gravitational force. Even with this possibility, the numbers remained tight. The object's brightness implied a surface too small for such prolonged heat release. Once again, the evidence refused to settle into comfort. As these debates unfolded, the community reached a silent consensus. Whatever 3I Atlas was, it represented a category yet undefined, a new class of celestial body, neither comet nor asteroid, behaving with the stability of something engineered and the unpredictability of something natural. That phrasing never appeared in official papers, but it echoed in quiet discussions among astronomers. Not speculation, just the acknowledgement that sometimes nature operates in ways indistinguishable from design. By then, the object's distance had surpassed 6 astronomical units, moving through a realm where sunlight fell like a pale memory. The faintest glimmer of its presence still appeared in specialized detectors, a thread of motion against the endless dark. For most, the active observation period was over. Funding would shift elsewhere, telescopes would point to new coordinates, and the archives of 3I Atlas would rest among the great unsolved cases of modern astronomy. But for those who had spent countless nights tracing its path, the object had already accomplished something rare. It had reignited humility, a reminder that even the smallest traveler from another star could unsettle the strongest laws written on Earth. And so, though unseen now, 3I Atlas continued on its silent course, farther and faster than before, taking with it the data, the questions, and the quiet awe of everyone who had watched it move. In the months that followed, the data surrounding 3I Atlas became the focus of deeper, more deliberate study. What had begun as a tracking project, an attempt to understand the orbit of an interstellar visitor, was now evolving into something far more intricate. Astronomers were no longer just watching an object move through space. They were confronting a pattern that physics could not easily explain. The strange acceleration that had haunted every calculation refused to fade, even after more than a year of observation. Every recorded position, every timestamp, every photometric curve reaffirmed the same quiet reality. Something was gently pushing this object, and no one knew why. To the untrained eye, the difference seemed microscopic. The variation in velocity amounted to only a few centimeters per second each day. But over astronomical distances, those centimeters built into kilometers, and those kilometers into millions of kilometers. Space magnifies everything, even the smallest uncertainties. It was precisely that magnification that made 3I Atlas so perplexing. The math didn't lie. It had passed through the solar system and was now moving faster than when it entered, as though space itself had given it an invisible boost. When data from the European Southern Observatory, NASA's Deep Space Network, and the Japanese Subaru telescope were compared, the match was uncanny. Every set of readings, collected from different hemispheres of Earth and with entirely different instruments, produced the same residual acceleration within a margin of only 5%. Such global consistency was unprecedented for a phenomenon that no one could yet describe. Teams that once competed for discovery credit now shared their data openly. For a time, the object united institutions across continents. They were not chasing glory, but understanding. Inside research facilities, the nights grew long with simulation work. The equations filled chalkboards, and the walls were covered with trajectory diagrams drawn in faint white lines. Scientists compared thermal models, surface albedo estimates, and density calculations, hoping that one variable might unlock the pattern. None did. The more they refined the numbers, the less sense the behavior made. The simplest explanations fell apart first. Solar radiation pressure was too weak. Gas emission was undetectable. Micron dust sublimation failed to provide enough force. Magnetic interactions with the solar wind were inconsistent with the direction of motion. Each test removed one more option until only uncertainty remained, and yet, for all that uncertainty, there was clarity in one respect. The acceleration was constant, gentle, and perfectly aligned with the object's flight path. It wasn't chaotic or fluctuating. It didn't pulse or shift. It was steady, patient, and eerily precise. Some wondered whether the object's composition might include unknown materials, elements formed under alien stellar conditions. Perhaps the crystalline structures or molecular bonds within it reacted differently to radiation, creating a continuous outward pressure invisible to our instruments. It wasn't fantasy. It was simple curiosity, an acknowledgement that interstellar matter, forged around distant suns, might not behave as anything found within our own. Others focused on its physical geometry. If the object were elongated, like a needle or a flattened shard, its interaction with light could create subtle but continuous torque. Even that, however, required reflectivity far beyond what the measured brightness allowed. The deeper scientists looked, the more elegant the puzzle became. It wasn't dramatic. It wasn't loud. It was simply perfect in its calm defiance of expectation. By this time, the data set of 3I Atlas had grown vast enough to sustain multiple doctoral studies. Dozens of papers were in review, each focusing on different aspects of its motion: rotational stability, density profile, reflectivity models, heat retention. But every conclusion ended the same way, with an ellipsis rather than a period. The mystery persisted. Even as interest in the general public began to wane, among the scientific community, the object had become an enduring whisper, a quiet reference in conference halls, an example of how even the smallest anomaly can shake the confidence of equations centuries old. Many of the astronomers who had tracked 3I Atlas since its discovery described a strange feeling of attachment. They had watched it enter the solar system, measured its closest pass, and then seen it drift back toward the stars. In a way, they had followed it like a distant friend whose presence was felt only through numbers and faint glimmers of light. When the final signal was confirmed and the object passed beyond the range of direct detection, there was no celebration, only a long silence. A silence filled not with disappointment, but with reflection. They had seen something extraordinary. A traveler from another sun, small enough to be missed by the naked eye, yet powerful enough to remind humankind how little it truly knows. In the deep archives of observatories around the world, folders labeled 3I Atlas, Anomalous Acceleration Dataset, remain open, their final lines unwritten. New generations of astronomers will someday revisit them, armed with better instruments, faster telescopes, and new physics. Maybe then they will find the missing piece, the quiet reason behind a motion that once seemed impossible. For now, the data sleeps, and the object moves on. Its path stretches toward interstellar space, unchanged, unhurried, and eternal. And though no human eye will ever see it again, its legacy lingers here as a question carved in starlight. How can something so small move faster than the laws of motion themselves? By now, 3I Atlas had vanished completely from the view of even the largest telescopes. The light that once reflected faintly from its surface was gone, absorbed by the infinite distance between stars. Yet, for the scientists who had spent countless hours following its path, the story had not ended. It had merely shifted into theory. The data it left behind became a foundation for new work, a library of equations, models, and unanswered questions that would inspire research for years to come. Teams who once competed for observation time were now collaborating on reanalysis projects. They fed every known parameter, velocity, brightness, acceleration, spin rate, into supercomputers, hoping that some hidden correlation would emerge. What they discovered was not resolution, but depth. The acceleration, as constant as it was, revealed subtle variations depending on the object's position relative to the ecliptic plane. It wasn't random, yet it didn't follow the simple rules of gravity or sunlight pressure. Instead, it seemed to drift along a line that no one had predicted, a faint, consistent offset that rotated slightly over time. That tiny rotation became the focus of a new round of studies. Some believed it was caused by the object's own spin, perhaps creating uneven exposure to sunlight. Others thought it might be due to magnetic alignment, though 3I Atlas showed no signs of interacting with magnetic fields. The effect was small enough to be invisible to casual analysis, but large enough to be real. It added another layer to a mystery already dense with possibilities. As the months turned into a second year, the name 3I Atlas appeared less often in press releases, but more frequently in research papers. It had become part of the scientific lexicon, shorthand for unexplained motion in interstellar objects. It joined Oumuamua in that quiet category of phenomena that sit between discovery and understanding. In conferences, scientists spoke carefully, avoiding speculation, yet unable to hide their curiosity. One group at the University of Arizona presented a detailed simulation showing that if the acceleration remained constant beyond the solar system, 3I Atlas would leave with a final speed nearly 2 kilometers per second faster than predicted. Over centuries, that change would alter the star systems it passed near, slightly bending the gravitational geometry of interstellar space. It was a humbling realization. Even something so small could, in time, leave a measurable mark on the galaxy itself. Elsewhere, astrophysicists debated the broader implications. If 3I Atlas and Oumuamua both showed unexplained acceleration, it could mean that such behavior wasn't rare. It was a property shared by many interstellar fragments, only unnoticed until we learned to look closely enough. Perhaps the cosmos was filled with objects quietly propelled by forces still unaccounted for. That thought lingered. The idea that invisible mechanisms might guide the motion of ancient fragments through the void. neither artificial nor magical, but simply unrecognized by our science, opened a new field of study. New telescopes under construction, like the Vera Rubin Observatory in Chile, plan to dedicate time to spotting similar travelers. Researchers developed detection algorithms tuned specifically to identify small anomalies in motion, tiny differences between gravitational models and real data. Every such detection would be another potential clue in the growing puzzle that 3i Atlas had started. But beyond the technical progress, there was something emotional about its legacy. For the people who had tracked it, night after night, its disappearance left a strange emptiness. They had spent months aligning mirrors, recalibrating sensors, adjusting coordinates, just to follow a faint point of light moving across the cold sky. And now, that light was gone. Some described the feeling as watching a ship fade into fog, knowing it was still there, still moving, but beyond reach. Others found comfort in the idea that the data it left behind was enough. Every number, every pixel, every fraction of velocity was a conversation with something that came from beyond the sun's light. Years from now, those same numbers might be reinterpreted, reanalyzed, and finally explained. But for now, they remain as they are, lines of data, frozen in time, recording the passage of a mystery no one yet understands. And somewhere, beyond the distant pull of our star, 3i Atlas continues its quiet journey. It travels without audience, without witness, through the vast corridors of interstellar space, carrying with it the questions that Earth once asked in whispers under the night sky. The telescopes have turned away, the calculations are stored, but the story is still unfolding, carried forward not in light, but in imagination, the enduring human desire to know what lies beyond the known. By the time the second anniversary of its discovery arrived, 3i Atlas had long passed from sight but not from thought. The object's name had become something of a symbol among astronomers, a reminder that even in a century of precision, instruments, and deep space observation, the universe could still surprise us with something quiet and inexplicable. In universities across the world, graduate students wrote theses based on its data. In observatories, archived files labeled Atlas 2025 remained open on computer terminals, lines of code and graphs, frozen mid-analysis, waiting for future work. The story had moved from observation to interpretation. What could a single interstellar rock, no larger than a hill, teach about the hidden structure of reality? When new analysis began, scientists approached the mystery from a different angle. They no longer asked what was pushing the object, but rather what the object itself revealed about the laws of motion. The key insight was subtle. 3. Atlas might not have been breaking physics, but exposing its edges, those faint, untested boundaries where theory begins to stretch. To understand that, researchers recreated the conditions of the object's journey. Simulations mapped the sun's radiation field, the solar wind, the distribution of dust, and even the gravitational pulls from passing planets. Then, into that virtual environment, they placed a model of 3i Atlas based on its observed brightness and spin rate. No configuration matched the real-world data. The models showed that for such acceleration to occur, the object's material must have had an extraordinarily low density, perhaps lighter than balsa wood, possibly porous, almost sponge-like in structure. It would have to reflect light with extreme efficiency, like polished metal, and yet appear as dim as rock. Those two qualities could not exist together without contradiction, and yet, there it was, drifting through the dark, behaving as though that contradiction were normal. The more they studied it, the more it felt as if 3i Atlas was a messenger, not in the poetic sense, but in the scientific one. It had carried information across the gulf between stars, encoded not in language or symbols, but in behavior. Its motion was the message. Every fraction of acceleration, every unexpected deviation, every unexplainable constant, all of it spoke of conditions and materials that humanity had never encountered. It was a sample not of matter, but of physics. The revelation spread slowly through scientific circles. Perhaps the key wasn't in finding what caused the push, but in understanding what made it possible. Maybe 3i Atlas was built, naturally or otherwise, of matter that interacted differently with light, gravity, or vacuum than anything found in our system. Not artificial, not alien, just unfamiliar. That idea marked a shift in tone. It replaced speculation with patience. Researchers accepted that explanation might take decades, perhaps until another such object arrived to be measured in the same way. And it would. The universe, generous in its repetition, had already sent two. It would send more. Plans were drafted for next-generation survey missions, space-based telescopes with wider fields of view, faster reaction times, and higher sensitivity would scan the sky for faint moving points like 3I Atlas. Instruments would be ready to record acceleration patterns from the very moment of discovery, not months later. This time, humanity would be prepared. Yet even as the focus shifted to the future, something remained deeply human about the way scientists spoke of it. They described its departure as if it were a farewell. They imagined it gliding silently through interstellar dust, its surface scarred by ancient collisions, its temperature just above absolute zero, a lone traveler, untouched and undisturbed, leaving behind the brief moment when it had been seen by eyes from another world. In lectures and documentaries, 3I Atlas was sometimes compared to a drifting ember, a glowing remnant of a fire that had burned in another star system, now floating endlessly between suns. That metaphor, though romantic, held truth. Every interstellar object is a fragment of a story older than Earth itself, a shard of memory from somewhere far away. And 3I Atlas had reminded humanity that such stories still pass quietly through our skies, unnoticed until curiosity catches them. Somewhere, at the edge of measurable space, it continued on. The faint push that had confused every model might still be acting upon it, steady, unbroken, unchanged. The same silent force that had carried it through our system could now be guiding it toward another. If it ever reaches another world, another civilization might notice the same anomaly, plot the same equations, and wonder, as we do, what invisible hand moves through the dark between stars. But for now, here on Earth, all that remains is data, numbers written in neat columns, equations etched in memory, and the quiet realization that something once passed through our corner of the universe and left us with a question we still cannot answer. The question isn't whether 3I Atlas was natural or not. The question is simpler, more profound. Why did it move that way? No one can say, not yet. But someday, when another traveler appears in the night sky, another faint light crosses the edge of our telescopes, humanity will remember this one. The first that taught us how even silence can carry meaning, and how mystery itself can become knowledge, one orbit at a time. And in that memory, 3I Atlas will live on, not as an object, but as an idea, the reminder that the universe is still unfinished, still full of questions waiting quietly. Beyond the light, the final data from 3I Atlas arrived in fragments, faint readings recorded by long-range instruments that captured the last glimmers of reflected sunlight before the object vanished, entirely into the deep interstellar night. After that, there was nothing left to see, only silence. But sometimes, silence says more than any signal ever could. For those who had followed the object from its first detection, its disappearance felt like the closing of a long chapter. They had watched it emerge from the dark, move through our solar system, and then fade again into the void from which it came. Its passage had lasted only months in the measure of human time, but in the scale of the cosmos, it was a blink. And yet, that blink had rewritten what scientists thought they knew about motion, matter, and the invisible laws that shape the universe. In the aftermath, a quiet revolution began. Every observatory, every research institute that had touched the 3I Atlas project started re-examining its data archives. If this visitor had shown unexplained acceleration, perhaps others had as well. Objects dismissed years ago as measurement noise or minor error. Teams pulled old asteroid data, comet records, and interstellar track logs from decades past. A few anomalies began to appear. Tiny deviations that once seemed irrelevant, but now stood out like subtle signatures echoing through time. It was becoming clear that 3I Atlas might not have been unique. It might have simply been the first one we had looked at closely enough to notice. Across the world, the phenomenon became known by a new informal term, the Atlas effect. It was shorthand for that faint, persistent, sideways acceleration that seemed to whisper through certain interstellar visitors. No one could define it yet, but everyone who studied celestial motion now knew the name. Conferences began dedicating sessions to the subject. Papers emerged proposing new physics, exotic materials, or forms of natural propulsion that required no energy source. One idea suggested that these objects might carry thin layers of electrostatic charge accumulated over eons in interstellar plasma, producing constant but minute thrust when exposed to solar wind. Another argued that the effect could arise from self-regulating surface chemistry, materials expanding and contracting with temperature in perfect equilibrium, generating movement too subtle to see. The theories multiplied, but all had one thing in common. They were born from 3I Atlas. For the younger generation of scientists, it became a symbol of persistence. It reminded them that science is not about having all the answers, but about learning to ask better questions. Each uncertainty, each anomaly, each unexplainable reading was no longer a flaw in the data, but an invitation to look deeper. And so, while the object itself drifted into the abyss, its legacy remained alive. It lived in lectures, in classrooms, in long nights under cold observatory domes. Professors would begin lessons on orbital dynamics by mentioning it, and students, born years after its discovery, would still know the story. Somewhere in deep space, 3I Atlas kept traveling outward. Its faint acceleration, if it still persisted, would be pushing it toward another star system, perhaps one it would never reach, but still moving with quiet precision through the endless dark. The same laws that confused humanity here would guide it everywhere. The same mysteries that humbled us would echo across light years of silence. No one would ever see it again. Yet it would always exist in the equations, in data, in the subtle changes it left behind in how we looked at the cosmos. For centuries, humans have looked at the night sky, searching for signs of life, of intelligence, of meaning. But sometimes the universe speaks differently, not with language or messages, but with behavior, with motion that bends expectation, with silence that carries understanding. 3I Atlas was one such voice, whispering across the emptiness not in words, but in wonder. Perhaps that's how the universe truly communicates, through patterns, through balance, through the questions that compel us to learn more. Years after its disappearance, astronomers still returned to its numbers. They plotted its orbit one more time, just to remember how it moved. And when they did, they felt a kind of calm, an appreciation for how small and vast existence can be at once. The same realization ancient stargazers must have felt, that the universe doesn't owe us explanation, only experience. In a distant research center, the final line of its data log still reads, 3I Atlas, non-gravitational acceleration detected, cause unknown. That single sentence is its legacy, a truth suspended in uncertainty, proof that even without answers, discovery itself can be enough. And so the traveler continues, unseen but not forgotten. Through cold space and eternal distance, it carries its mystery onward, as all things in the universe do, quietly, faithfully, beautifully. We may never know what pushed it, but we will always remember that it moved,